In this week's lecture, I'm going to talk about network traffic flow theory and characteristics. So the main question of interest here is we would like to explore the physics of traffic flow in urban networks. So far, we've learned about the physics of traffic at sections on the road or at link level. We learned about the traffic flow fundamental diagram. We learned about the traffic flow fundamental identity. We learned about models like green shields. We learned about the congested and uncongested branch in the fundamental diagram, shock waves, a little bit of hysteresis. And we learned that it's not necessarily just in car traffic. The same phenomena and characteristics can be observed in pedestrian traffic, for example. We learned about how to calculate flow, speed, density at the link level or when we're looking at a section of the road. But now in this week's lecture, we're going to look at an extension of all those two networks. So if I want to give you some classical background here of different levels of traffic flow modeling, we usually have macroscopic, microscopic, and mesoscopic levels of when it comes to traffic modeling. So in the macroscopic case, we look at aggregate relationships between flow density and speed. Very similar to the fundamental diagram, right? So for example, the speed flow relationship, which is all about aggregation, right? We aggregate over, for example, 5 minutes or 15 minutes, and then we compare those numbers. Microscopic is when we model individual behavior of cars, like the car following models that we learned, that two individual cars are following, there is a follower, there is a leader, there is a headway between the cars, calculate each individual car acceleration and speed. So that's a very microscopic way of looking and modeling and measuring traffic. There is a level in between macro and micro, which is called mesoscopic. Mesoscopic describes the dynamics of individual vehicles as a function of aggregate relationships. So again, we haven't covered much of mesoscopic in this course, but to give you a bit more of intro here is, in mesoscopic models, just like microscopic, we still model and simulate individual cars, but instead of using car following model, for example, we use a fundamental diagram to move the cars. Or any other aggregate function to move the cars on links. So that's the difference. So that's why we say it's mesoscopic sits somewhere between macroscopic and microscopic. A little bit of refreshing our memory on traffic flow fundamental diagram and ED's definitions, if you remember. So we said if you have a time and space diagram with trajectories like this, if you specify a region in this time and space diagram, any region, it could be a rectangle, it could be a polygon or a circle, or just any weird shape. If you want to calculate flow within that region, flow within that region would be the summation of the distance traveled by all trajectories divided by the area of that region. Density would be the summation of the travel times within that region divided by the area of this triangle. And a speed can be calculated using the traffic flow fundamental identity, Q equal KV. So V is equal Q over K, right? We use the traffic flow fundamental identity to calculate the speed. And then if we plot flow, speed, and density against each other, we get what is known as traffic flow fundamental diagrams, the relationship between a speed and the speed, density and a speed, flow and a speed, density and flow, which can be modeled in many different ways. We could go with a triangular flow density relationship. We could go with a green shields model. I think in one of the quizzes we had, you were exposed to some other flow density relationships. We learned about the the physical mechanism of traffic jams. Let me see if I can show you this original video. I'm not sure if I showed you this, but this is, if I show you both the paper and the experiment. So let me take this out, and so this is an experiment. Let me show you the title again. This is an experimental evidence for why traffic jams form on a road by a group of Japanese scientists. And they wanted to show that we don't necessarily need to have a bottleneck on the road to see traffic jams. Without bottlenecks, without incidents, we can still have traffic jams. So they set up a ring. They had a couple of cars were instructed to drive on this ring. And as you can see, drivers gradually start, and they were asked to drive in with the same speed. But because driver behavior is not perfect, some drivers were going slower, some drivers were going faster, and that over time has led to creation of stop and go waves or shock waves, basically. And you'll see the formation of shock wave here. If you look at the ring now, you can see that the shock wave is actually moving backward here. Look, vehicles are stopping on the left side of the ring. So they stop, it's a stop and go wave, and then a shock wave basically gets created. Oh, I wanted to show you the actual paper, sorry. It's a really nice paper to read, I would say. It is published in, I really recommend you to have a look at this paper. Look, it's published in a physics journal. I think I told you about this, that traffic engineering, or basically, actually not necessarily it's engineering, traffic flow theory, traffic flow characteristics is an interesting field that it's not just an engineering field. Many people from science, especially from the physics community, also work on this topics, because we see similar phenomena in other systems. Like there's something called granular flow. Imagine you have wheat. Let me actually find a granular flow. Granular flow. So look, if you have some wheat or soil, or I don't know, anything else that is granular, or rice. Look, let me actually see what this one is. I want to show you how physicists look at these phenomena. So forget about the measurement method that this guy is using, but this is a granular flow. I think he's using rice here. So he's pouring some rice into that little container there. Is that rice, or maybe it's something else? I'm not sure. But anyways, again, if you search for granular flow, you'll see many examples online. Yeah, look at this. How things that are granular flow in different environments. So physicists use the same perspectives, or fundamentals in the general granular flow, and they try to study car traffic, because again, they could view car traffic as granular flow. But anyways, so have a look at this paper. It's a very nice paper published in New Journal of Physics back in 2008. So you see, it's not super old. So it's only maybe 10, 12 years old. If I open the paper, let's see what they studied actually. I want to see what kind of graphs they produced. So make sure you download this paper, have a look. So they start by talking about the fundamental diagram, a relationship between flow and density. You see, we have this uncongested branch on the left, and then the congested branch on the right. They talk about their experiments and how they created that. Then they show the vehicle trajectories. You see how shock waves have formed and is propagating backward. Here's another example that a shock wave has formed, and they actually calculated the slope of the shock wave, which is 20 kilometer per hour in this case. And that's it. It's relatively a short paper, but they just want to show shock waves can form out of nowhere, just simply because drivers are not driving perfectly. So I talked about this, but now the question that I would like to ask is, do we think urban networks have also a similar fundamental diagram? So what we've seen in that video of Sugiyama and that paper, the classical paper of the ring road, it's only a ring. It's not a real network. It's not a big, large urban network. The fundamental diagram that we measure from loop detectors, it's also only a section of a road. But do we see a similar fundamental diagram for large-scale urban networks? The answer is actually yes, but let's see. Let's first try to measure something. Let's first try to measure the network-wide average flow and density and speed. So how can we calculate network-wide average flow and average speed? One simple way is, imagine we have this network. This is actually a real network from Irvine, California in the US. So it's a small suburb in California. It has three major freeways. I guess this is one freeway, this is one freeway, and this is another freeway. The rest is urban arterials. And you can see we have maybe hundreds of links or tens of links in this network. One easy way of calculating average flow and average density is that to take the weighted average of flow across all the links, weighted by the length of the link. So here, look, imagine we have 100 links. And each link some of the links are 1 kilometer, some of the links are 2 kilometers. And we have the flow on each individual link. If we take the average of all these flows across all these links, weighted by their length, then that could give us the average network-wide flow. So look at the formula here. So this is the individual link. This is the individual link flow. This Li is actually the length of the link. And so it's a weighted average. So we weight the flows are weighted by the length of the links. And obviously in the denominator, we have the summation of all the link length. So this is the summation of all the link length, right? So this weighted average of flows weighted by the length of the link will give us the capital Q, which is representing network average flow. We can also use a similar approach to calculate network-wide average density, where we have individual link density and the length of the link. Same thing, divided by the summation of the link length. And that would give us the average network density. And if we plot them against each other, if we plot this capital K versus capital Q, we want to see, will we be able to see a similar curve as we've saw before in fundamental diagram? And again, the answer is yes. And there are empirical evidence and simulation-based evidence that suggests that a similar diagram exists at the network level, which is called network fundamental diagram, or it is also called macroscopic fundamental diagram. So we call it MFD or NFD, which says This is capital K, capital Q. So if you take the average network density and average network flow, and if you plot them against each other, you will be able to see a nice curve like this, which looks very similar to the fundamental diagram, but with slight differences. It is less scattered. You see, if you remember the traffic flow fundamental diagram, the actual data was on the congested branch. It was very scattered, right? While MFD, if it meets some criteria, it is usually called well-defined or with less or a very low scatter. And what it suggests, it suggests that if the average density across the whole network is something, we can actually estimate what the flow would be. There is also another way of calculating this average network-wide flow and density, and that is using the extended extended ED's definitions to the 3D time and space diagram, similar to what we've done in pedestrian traffic in the last lecture. If you look at a 3D time and space diagram like what we see here, and if we have trajectories going from origin to destinations, what we can do is we can use that extended ED's definition and try to calculate network-wide average flow and average density, where the only difference here with pedestrian traffic is that in pedestrian traffic, if you remember, that cube measurement, that cubical measurement area that we were looking at, we said Q would be the summation of the distance traveled of all the trajectories within this cube divided by what? The volume of the cube, right? So this was for the pedestrian case. It was the volume of which was x, y, t, right? So the denominator was the volume of this cube. But this, we derived this equation because it was pedestrians, and pedestrians could go multi-directional. There's actually no lane or anything to follow, so they can go in any direction they want. But when it comes to car traffic and in the context of urban networks, vehicles are constrained with the streets, right? The road network. So vehicles can only drive within the bounds of the street network. So look at the bottom part of this box here. So this entire area is not available for vehicles to move around, right? Vehicles can only move on the streets, right? So that network that I'm drawing on the bottom of this cube is actually like a street network. So instead of having the volume of the cube in the denominator when we want to use the 3D trajectories in calculating for calculating network flow, we use the length of the network. So this capital L here is the total length of the network in that measurement area, in that cube. So for example, if I have 100 links and each of them is 1 kilometer, the total length of the network would be 100 kilometers. If I have 100 links in this network, 50 of them are 2 kilometers and 50 of them are 1 kilometer, it would be 100 plus 50, it would be 150 kilometers. So this would be my capital L. It's the total length of the network within that measurement area. And this TV is the delta T. It's similar for in pedestrian traffic as well. So that's my delta T of measurement. If you want to do every 5 minutes or every 15 minutes, that's the delta T that we're using here. So it's the same concept, it's the same formula, except that instead of using the whole volume of the measurement cube, we use the capital L, network length, multiplied by my delta T, the temporal aggregation level. Similarly, we can calculate average network density, where we have, this would be the summation of the distance traveled, the summation of the travel times, so flow would be the summation of distance traveled divided by that, and density would be the summation of the travel times of all the trajectories going within that, entering and exiting this cube, divided by the same denominator. So that's how we can also calculate average flow and average density. It's a little bit more data intensive, I would say, because if we want to go with this ED's definition, we need to have individual trajectories, right? So that's a lot of data. But a simpler way is just to go with the weighted average, as I shown here. And here are some examples of how these 3D trajectories in a real urban network look like. So this is the same Irvine, California network, where we look at it from the top view. So look, it's X and Y. We look at it from the top view, and now if I rotate this, and if I look at it in the 3D time and space diagram, I have X, I have Y, and Z axis is my time. I see all these trajectories going around, just like this hypothetical graph that I had. So trajectories will move in this time and space diagram. And what are all these trajectories following each other, creating something like a wall? These are representing the freeways. So because the volume of the freeway is high, so if this is one freeway, this is another freeway, and this is another freeway, we had three freeways here. Because the volume of those freeways are high and vehicles are very following each other closely during rush hour, we see something like this in the time and space diagram, that there are a lot of trajectories following each other, and they kind of create a surface or plane representing that large roadway. But anyways, that's an example of a 3D time and space diagram when it comes to network traffic. So, but before we dive into some more content here, let's step back and have a look at a very simple network. Imagine we have a two-link network, probably the simplest network ever, right? So we have an origin, we have a destination, and we have two links, A and B. And let's assume each of these links, so link A and link B, they have a triangular fundamental diagram, which with KJ and QC and this KC, right? It's actually here, so I don't need to redraw it here. So this fundamental diagram that you see here is the fundamental diagram of link A and link B. And link A and link B are identical. So they have the same length, they have the exact same fundamental diagram. Now let's try and plot the MFD or NFD. Let's plot the network or macroscopic fundamental diagram for this entire network. It's a small network, but it's a good practice. So let's see. If link A has zero flow and zero density, and link B also has zero flow and zero density, so both A and B falls here, right? So what would be the average flow and average density? It's the same, right? So let me draw it this way. So I have capital Q and capital K. So in this case, it would be 0 and 0 for the network as well. Now imagine A is here. Imagine this is A. Imagine this is B. So A and B are both uncongested, right? They are on the left branch of the fundamental diagram. So what would be the average flow and average density here? So the average flow and average density actually lies somewhere between, right? If you want to take the average of these 2 points, so this would be capital K, this would be capital Q. So I would say capital Q is still I don't know, let me put a number here. So let me erase some of this. So yep. So this is A, this is B, and this one, in the middle, which is the average, is, let's call that Q1, and here would be K1. So let's call that Q1 and K1. So it falls on the fundamental diagram, right? So I have this point, I have this point. I'm still on the same fundamental diagram at the link level, right? So if I want to plot capital K versus capital Q, so this is FD, this is MFD or NFD. So this was link fundamental diagram. On the right, I'm gonna draw the network fundamental diagram or macroscopic fundamental diagram. So I had 0, 0, I had Q1 and K1. So far, it just follows the same triangular fundamental diagram, right? Let's have a look at another example here. So imagine this is A, this is B. So link A is congested, link B is also congested. They are on the congested branch of the fundamental diagram. What is the average network? What is the average flow and average density in this network? It would be simply the weighted average of the densities and flows, right? So the average also falls somewhere in between, which is again exactly on the fundamental diagram. So let's call that K2 and Q2. So Q2 and K2, and that is also, let me also just draw it here. So that would be my Q2 and K2. This is my Q1 and K1. But now let's make a different example here. Now imagine link A is congested while link B is uncongested. So let's have a look. So imagine this is A, link A is congested with a very high density and whatever flow, and this is link B. Where does the average lie? If I want to take the average density and average flow between A and B, it would be somewhere in the middle, right? So interestingly, let's call that Q3, K3. When A is congested and B is uncongested, interestingly, this point, this average point at the network level, no longer lies on the link level fundamental diagram. So I will have a point here. So Q3, K3 would be here. And we can go on and on. So if I have one, now imagine imagine this is A. Imagine A is uncongested and this is B. B is congested. So where does the average lie? Average lies here, right? Which would be Q4, K4. So there's another point here. So look, these are now my new points in the fundamental diagram. So it's not necessarily well defined, as I said before, right? So by this example, I wanted to highlight the conditions for the MFD or NFD to remain triangular if the link fundamental diagram is triangular, or in a more general term, it remains well defined or with low scatter. In this example, I just showed you that we can have a lot of a scatter. The points can be all over the place. The average points can be all over the place. But what is the condition for the MFD to remain well-defined and with low scatter, or remain triangular if the link fundamental diagrams is triangular? The condition is that the traffic must be distributed homogeneously in the network, meaning that at any time, all links should be either simultaneously congested or they should be simultaneously uncongested. So let's have a look at this example again. So in the case where A and B were both uncongested, we saw that the average was lying on the fundament on this triangle. When A and B were both congested, the average was here, right? So you can have many other examples. If A and B are here, the average is here. So as long as A and B are simultaneously at the same time, are both congested or they're both uncongested, the average flow in the network and the average flow of average density in the network will lie on the same triangle. So then the MFD in this simple hypothetical example will be exactly the same as the fundamental diagram. But again, this happens because these two links are identical. If they had a different length, if they had different fundamental diagrams, the MFD would not exactly be the same as the fundamental diagram, but it could still be low scatter and well defined, um, uh, but slightly different than the original fundamental diagram at the link level. But anyways, this condition is very important. So just wanted to highlight this, that if we want to see an MFD that is low scatter with no hysteresis and well-defined, traffic must be distributed in the network homogeneously. I think I talked about this. And now, if we expand this example, imagine I make 100 more examples of different scenarios where A is here, B is here, A is there, B is there, and take all the averages. What I will end up having is that I will end up having this trapezoid. Very interesting phenomena. That so this is capital K. This is network density. This is network flow. So this shaded area is the area where the average flow and average density points could lie. So I can have a scatter here. If that homogeneity condition is not met, I could possibly have many average flows and average densities lying in this trapezoid. So when traffic distribution is not homogeneous, network level measurements of flow and density can fall below this theoretical triangular MFD in this case, in this two link network example, link A and link B. If we had a perfectly homogeneous traffic distribution in the network where link A and B were at the same time congested or at the same time uncongested, MFD would exactly be this triangle that I shaded, that I highlighted. But if this traffic distribution homogeneity, this condition is not met, my measurements of network flow and network density could just be in this shaded area. And this shaded area is, it can be called as an unstable area, or it could be called as the area where hysteresis occurs, right? So hysteresis is, for those of you who may not remember from the previous lectures, hysteresis is where if the network, if something goes, if the relationship between flow and density looks like this, when density is increasing, hysteresis is a phenomena that if now density decreases, we can either come back on the same line, right? So going up and going down will superimpose, or we can come back on another way. So if the path that we are traveling in this fundamental diagram, when density is increasing or decreasing, is not on the same line, that is called hysteresis. So this is called the hysteresis here. So this shaded area here represents the area that a hysteresis could form. We can, so if I want to show you, so for example, I can go up and then I can come down. I don't necessarily come down on the same path that I was going up when density was increasing. There's also, and now imagine so this was for the two-link network. Now imagine we extend this to an n-link network where we have n links. So all these calculations that I've done here, where this point of the trapezoid was half of QC, this point of the trapezoid is half of KJ, and this point is half of KJ plus KC. I mean, all of these we can derive. It's not very difficult to derive. All of this will be extended to an n-link network. So this is a network with n links, and you can see that the trapezoid is the polygon that we had here. The trapezoid is now has the size of that polygon has enlarged, and now we have a larger area, shaded area, and you can see that now we have a more general calculation of these corner points of this polygon. But um, and just want to highlight something, that there is a phenomenon also called bifurcation. Bifurcation is a point. This is bifurcation point where for any traffic density, imagine for K1, for any value of density, we may have multiple value of flow. So look, if this is my fundamental diagram, if I have a hysteresis like this, that I go up and then I come down this way. So look, for K equal, let's say 10, flow could either be this much, Q1, or could be Q2, depending on whether it's on this side of the MFT or it's on this side of the MFT. This is called the loading side versus the unloading side. But anyways, this is called the bifurcation point. And another interesting thing here is that imagine the network is very, very large. Imagine n goes to infinity. What will happen? So look, what will happen to this bifurcation point? If n is a very, very large number, infinity, this means we'll have 1 over infinity, which is almost close to 0, right? So this means the bifurcation point will be pushed down all the way to this 0 point. Same thing here. If I have 1 over infinity, this means this point will be pushed to the left all the way to the origin, and this point will be pushed all the way to this kj. So when a network is very, very large, what does it mean? What does it mean in terms of the traffic homogeneity distribution, traffic distribution homogeneity, and possibility of seeing a scatter in the MFT or hysteresis? This shaded area basically covers the entire area underneath this theoretical MFT, the triangle. So that means we can have a scatter anywhere. If the network is super large and the condition of traffic homogeneity is not met, we can have my average flows and average densities anywhere under this triangle. And then obviously we can have some transitions between different phases. So imagine I have this theoretical MFT triangle here. So this branch can be called a free flow phase, where when all the links in the network are free flow. This branch on the right can be called homogeneously congested. That means, so this is called homogeneously congested. That means all the links at the same time are congested. So we can have transition from F to HC. We can have transition from HC to F, right? But if that homogeneity condition is not met, my average flow and average density could be anywhere in this shaded area. And that's what we call inhomogeneously congested phase. So IC represents, stands for inhomogeneously congested. So if a transition from F to IC happens, that's a hysteresis. If a transition from IC to F or F to IC or IC to F happens, that's what we call hysteresis. But let's have a look at some real data, and let's move on from some theoretical stuff that we've gone through, and let's move on to some real data so you actually see how does it look like in reality. So but before that, let's take a break. It's 11. So let's take a 5-minute break, and then we'll come back, and then we'll continue with looking at some empirical data and trying to calculate average flow and average density and see how the actual MFTs